So today I'll be introducing you the additive manufacturing. So some of you may be already aware about it. So why I thought of introducing you additive manufacturing, because tomorrow Professor Mario will be teaching about the impact of short peening on additive manufacturing. So that you might have seen in the schedule. So I thought that as we do have some of BTech first year students as well as MTech first year students, so I thought that I'll be introducing the additive manufacturing in detail to you so that you will be able to understand and follow tomorrow's sessions well. So that is the whole intention behind my today's talk. Okay. So have you all heard about additive manufacturing? Yes. So what is additive manufacturing? Let's have an interactive session rather than listening to me for the entire 1.5 hours. I don't believe in that. I'll be asking a lot of questions based on what I am telling. So I want all of your presence of mind. Okay, not simply listening to the slides. I know it is little difficult because it is in the afternoon sessions. You all had food and it will be a little difficult. I know that, but you have to cooperate with me. What is additive manufacturing? Can anybody define additive manufacturing? Be loud, be loud. You can come closer. So that would be better. Come closer. Otherwise, you have to be so loud. You guys also. Come. Sit in front. Not that row. First, second rows. First and second. First and second. Here also. Come, come. First and second. 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 Those who are not coming to the first, nobody is ready to come to the first row. Why? You guys can come. So easy to hide behind the camera, right? Okay. So now let me know, what is additive manufacturing? What is additive manufacturing? If you are not telling, I will ask you individually. What do you guys know about additive manufacturing? Addition of materials, yes, exactly. One thing is addition of materials. That's fine. So anything else that contribute to the definition? Have you heard about additive manufacturing? No. Have you heard about 3D printing? Yes. So the 3D printing is known in another way, that is called as additive manufacturing. Both are same. Okay, both are same. So it is layer by layer manufacturing. Other than that, if it is layer by layer manufacturing, it's all called additive? No. Why? There are so many layer by layer manufacturing process, all of them are not called as additive. Why? So then in order to qualify a process as additive manufacturing, what it has to be? So in what scenario we can call a process? In what scenario we can call it as an additive? Be loud, be loud. Same kind of materials. Not exactly. So what he said is layer by layer. That is fine. That I do agree. Okay. Okay, let's forget about additive now. So let's come back again little basic. So have you heard about manufacturing processes? Additive manufacturing, we are putting it in one of the subcategories of manufacturing processes. So how do you classify the manufacturing processes as whole? Traditional and non-traditional. That is in, especially we do say in machining processes, right? I'm talking about the manufacturing as a whole. Have you heard about formative as well as subtractive manufacturing processes? No. You haven't heard about it? No. How do you classify the manufacturing process? How do you classify? Then our whole 1.5 hours will be over like this. How do you classify the manufacturing process? If you have not heard about formative as well as subtractive manufacturing process. Can you tell at least some of the examples for manufacturing process? Sand casting, forging, extrusion, rolling. I didn't hear. Milling. Okay. There are so many manufacturing processes. Okay. Including the peening, short peening. That is also a kind of a manufacturing process which is used for the surface treatment. So all these processes, one of the general classification for all these processes, one is formative manufacturing process and another one is subtractive manufacturing process. Okay, otherwise we can classify them in other ways. So that is called as the forming process. In the forming process, we can again subdivide them using by looking at the form of your raw material. Suppose if your raw material is in the form of a powder, it is powder metallurgy process. And if you are converting your raw material into liquid, then that can be a casting process. And if you are using a solid raw material and you are making the primary shape, then that is a metal forming operations, the conventional forming operations. One way of classification, that is one, that is forming. Then we do have machining operations or a metal cutting operations or a subtractive manufacturing process. Then we do have metal joining process. Then we do have regenerative manufacturing processes. So additive manufacturing comes under the last one, the formative manufacturing process. Okay, anyway, so let's forget about all these things now. Now I just wanted to introduce you some of the market trends in industries. So how do you prefer? So how do you think that the a preference of a customer in the market, whether it will be different from one person to another person or a group of people will be having the same preferences. So nowadays, if you look at the market, so everybody is in buying individual personalized products. Everybody's preferences are different. Do you agree with me or not? Everybody's preferences will be different in different ways. Maybe color differences, maybe the shape differences, or the functionality differences, all these things. So if you're doing a business, then you need to meet these customers' changes. Isn't it? The changing behavior you need to meet, or the customer's difference in behavior that you need to meet. So for that, nowadays in industries, we do have, see, initially everything started with a craft production, then it has gone for a mass production, then from mass production to mass customization it came. Now the trend in the industry is to produce or release the components that is very, very personalized things. Okay, so suppose if you are taking an automobile, so his preference will be something different. The industry has to make and design and fabricate an automobile or a car only for him. When it comes to the next person, it has to be designed and fabricated and manufactured for his needs. Is it possible? Is it possible? How it is possible? Because manufacturing entire setup will change to some extent, not exactly, to some extent. Okay, if you are simply changing the color, that is fine. But if you are changing the design, the engine capacity, will it be possible? It's difficult. But this is called as the flexibility. Okay, flexibility for your manufacturing process or the manufacturing facility. So that means if you are producing a shift, then immediately the entire manufacturing system has to be switched over to another model. But that is not happening in industries. So the ideal model should be like that. So that is called as the 100% flexibility. That is not exactly possible, but to some extent it has to be possible. So in order to make it flexible, we need our manufacturing processes has to be flexible enough. That means if you are making a component now, the next component should be a completely different one. Will it be possible? Suppose if you are making a cylindrical shaft using one machine, for example, you take lathe. In a lathe operation, you are making a cylindrical or cylindrical shaft. Immediately, will you be able to switch over to a gear? Because gear cutting may not be possible in a lathe. So that means that is not flexible enough to make that components. But when we are going for additive manufacturing, that gives us that freedom. If you are making a design right now, the next component that can be something different. So additive manufacturing gives us a lot of flexibility in terms of the production. Okay, that is one of the advantage of going for additive manufacturing. That means in order to meet this personalized production, in order to make the manufacturing processes flexible for the personalized production, additive manufacturing to some extent, it will help us to some extent. Okay, with machining processes may not be capable enough to do that. So this is what I was telling. So whenever we are going for the mass production, in all the industries, they do prefer to go for mass production because the individual product cost will be low, isn't it? Whenever you are making one component, the cost will be higher. But if you are going for 1,000 components, obviously the cost will be less. That you experienced whenever you are trying to buy one component, it will be less. I mean, very costly. But if you are going for 1,000 component of the same product, you may get it with a lesser price. That's what this graph shows. Whenever the customizations, whenever you are going for a low customization, the mass production will be, the mass production if you are going for, the cost will be less. And whenever the customization is higher, that means if you are trying to reduce the number of the component that you are ordering, so then the product cost is also getting increased. But our intention here is, see, we need to make the highly customized components with very low cost. Okay, so that means you need to get a freedom for customization. Okay, that is what all in the looking forward. So when we are looking at additive manufacturing, to some extent additive manufacturing gives us a good flexibility. In addition to that, additive manufacturing gives us this many advantages. After that, I will tell you what is additive manufacturing. Okay, so additive manufacturing provides us this accelerated time to market. That means we will be able to release our components very fastly into the market because of the rapid typing possibilities. So that is possible. Then instead of having a centralized manufacturing facilities, suppose if India, manufacturing facility in India, instead of that, we will be able to have a distributed manufacturing facilities. Another advantage is that the supply chain consolidation. That means suppose if you are making an engine in a conventional way, if you require 1,000 components to be assembled together to get that engine, if you are adopting additive manufacturing into your production, so what advantage we do get is, instead of 1,000 components, we can integrate more than 1 or 2 components together, maybe 5 components or 10 components. So that can be integrated as a single component, and that can be fabricated through additive. Okay, so the number of components that the company need to be transported to the assembly line will be lesser. So that advantage we do get. So that means supply chain consolidation. Then the design freedom. So some components we won't be able to, or it is very difficult to fabricate through conventional manufacturing process. But that designs will give us a lot of efficiency in conventional, in the design. Suppose in working environment, that gives us a lot of advantages. But we are not able to fabricate that in the conventional ways. Okay. So in such cases, the design engineers need to compromise with the manufacturing engineers to change their design to manufacture it. Okay, so they need to compromise the efficiency or compromise on the functionality. Okay, so with the help of additive manufacturing, without compromising, whatever the design engineers are designing it, that we will be able to develop it. Okay, so that is what it is called as design freedom. Okay, design freedom, we will be able to get it, and mass customization, that is possible, and low and mid volume production. And this process is not currently possible to be applied on a mass production scale. Okay, this is nowadays it is developed efficiently to a level of low and mid volume productions, not for high volume productions. So if you look at it, the industries where additive manufacturing is positively impacted, that means its impact was maximum in the design industry. The way we are designing with a conventional, the way we are designing for the conventional manufacturing, it's completely changed. Okay, with the help of additive manufacturing. And next impact is in the production and in the tooling industries. Then it is in the small scale productions, large scale production, supply chain also it is impacted, and so on. Okay, so it is more related with the design. The way we design the components is for different applications are changed with the adoption of additive manufacturing into conventional, into the as a manufacturing process, when we are adopting 3D printing as a manufacturing process. So here I'll just give you a comparison between the two processes, that is the subtractive manufacturing process and the additive manufacturing process. The first one, the A. So in the case of subtractive manufacturing process, what we do is we do take a block of material. How we are making a 3D component from a the subtractive manufacturing process, we do take a block of material, and then we do remove the material layer by layer in the form of a chip to make the 3D component. And what we are ending it up with, we do get a 3D project, 3D object, and also we do get lot of waste material in the form of a chips. Right, there is a lot of material wastage. But in the case of additive manufacturing, we do take the material in the form of a powder or a wire or in any other forms. We do take it. Then we are applying additive manufacturing processes. Then we do directly make this 3D object in a layer by layer fashion. So ultimately you end up with the 3D object, as well as the waste will be significantly low. Okay, significantly low. From the figure itself you can see that the waste, it is demonstrated in the form of a schematic diagram. Okay, very less material. We cannot say that there is no wastage, but to some extent there is no wastage. So in that way we can say that it is one of the environment friendly process, a sustainable manufacturing process. So here you can see that the first additive manufacturing machine, which is fabricated in the year 1987, okay, it is developed by the company called, it is released by a company called 3D System. It is based on a technique called UV photopolymerization process. It is comes under the category of watt photopolymerization. Okay, that was the first machine released in the market. Okay, it is again developed in an educational institution. And now we are having more than additive manufacturing process. It is applied to the materials. The first machine that is released only on the polymer based materials. Now we do have lot of additive manufacturing machines that can be applied for different kind of metals and alloys. This additive manufacturing got a global recognition or global attention year 2013 when Barack Obama prized about additive manufacturing in one of his United States addresses, Senate address. Okay, what he has mentioned is additive manufacturing has the potential to revolutionize the way we do make everything. Okay, So with this statement, he started his address and he has established 15 additive manufacturing hubs in US and followed by a lot of additive, the US industries as well as US Air Force, US Navy, in National Science Foundations, and so many other funding agencies started investing, including NASA. They started investing a lot of money on the additive manufacturing research. So that has made a requirement to develop a lot of additive manufacturing capabilities across the world, so that so much companies, software companies came in, so many other well-established companies have started investing money in that by understanding its potential. So it's became a rapid evolution of additive manufacturing. Research is started in the world because before 2015 we were not knowing about additive manufacturing a lot. It was there, even in NIT Calicut, we were having rapid prototyping machines since 2006 onwards, but there was no much research was happening. But now that is not the case. We do have a lot of research is happening in the area of additive manufacturing. Okay, because since 2006 to 2015 or 2008, 17 or 18, maybe since 2020, there was no much research on additive manufacturing. I'm talking about NIT Calicut situation. Okay, but now the scenario has completely changed. The worldwide, lot of research is happening. So all these driving force was happened because of this address. So let's come back to the definition which I have asked previously. So according to ASTM F42 committee, the additive manufacturing is defined as the process of joining the materials to make the objects from a 3D model data, usually layer upon layer, as opposed to formative or subtractive manufacturing methodologies. So whenever we are trying to call process as an additive manufacturing, it should qualify this definition. Okay, otherwise it cannot be called as an additive manufacturing process. Even though there are so many processes which is having the methodology as layer by layer fabrication, in many cases we don't call them as additive manufacturing because the process or the methodology does not start from a 3D model data. It is compulsory that if you want to call a process as an additive manufacturing, it has to start with a computer digital model. Okay, the process or the methodology has to start from a CAD model. Okay, so not only about this additive manufacturing, this similar technology was known in different parts of the world in different names that you can see in that figure. Some places it is called as layer by layer fabrication, some places it is called as 3D fabrication, 3D printing, some places it was called as rapid prototyping, some places it is called as additive layer manufacturing, some places it is called as solid freeform manufacturing, some places it is called as digital manufacturing. So that is one of the reason why ASTM has come up to form a single name on it. Okay, so that's why they have come up with this particular name, additive manufacturing. I hope you guys understood. Okay, so according to this definition, if you look at it, in order to call a process to be qualified as additive manufacturing, it should be a process of joining the material. It should be starting from a 3D model data. It should have preferably a layer by layer build approach, and it should not follow a subtractive or a formative manufacturing methodologies. So there are similar technologies okay, to additive manufacturing. Welding is a joining of materials, but it is not additive manufacturing. So 5-axis CNC milling, we will be able to make 3D objects, but that is not additive manufacturing. Similar way, you can look at it. So these processes which I have listed, it is some similarities as with the definitions, but it is not qualifying all the conditions. Okay. And this is again a comparison between the all the definitions as well as the definition requirements, that is the 5 definition requirements, as well as with the various processes. Whether it is, wherever I have put a y means that is yes, that particular condition it meets, but wherever we are keeping no, so that is not in those conditions. So we cannot, until you don't get all the rows as Y, you cannot call that process as an additive manufacturing process. So let's look at some of the advantages of additive manufacturing. So here it is. See, whenever we are trying to adopt additive manufacturing, so in the figure you can see that in the x-axis it is the batch size, that is the number of components that you are trying to manufacture, and the unit cost, the cost of single component. See, in conventional manufacturing process that we have seen in the previous graph, whenever you are trying to increase the number of the components, the cost will come down, right? But in the case of additive manufacturing, this is selective laser melting and is one of the additive manufacturing process. Okay, you can simply assume that this is additive manufacturing. In the case of additive manufacturing, it's almost a straight line. There is a slight difference, but almost a straight line. Whether you are making one component or a 100 component, the cost of production is going to be almost similar. So suppose if your number of quantity that you need to be fabricated in this region, then additive manufacturing gives you lot of advantages. So that's what I have previously told, that this particular technology is not for mass production. Okay, so especially in the areas like aerospace or in biomedical industries, the number of components that we are fabricating is very, very less. We are making 3 or 4 rockets in a year, right? So we require only 3 or 4 engines a year. Okay, that much component only we required. So the number of quantities that we are making is less. Similar way, if you are going for a biomedical industry, suppose if you wanted to make a implants, a personalized implants. Okay, so that means every person's requirement will be different. Every person's bone anatomy will be different. So you are making one component. Your production number of quantity is only one. In that case, additive manufacturing gives us a lot of advantages. That means we can say that individualization is for free to some extent. So similar way, the complexity. So whenever the product complexity increases, the cost of production will be increasing. So but in the case of additive manufacturing, you see, it will be almost a straight line. Okay, whatever the complex part it is, as it is a layer by layer fabrication process, the complexity is not at all matter. So cost is not going to change with respect to the complexity of the component. Suppose if your complexity is somewhere in this region, then additive manufacturing gives us a lot of advantages. That means we can say that complexity is for free. But we cannot say that there are some components even still cannot be fabricated through some of the additive manufacturing process. Okay, anyway, we will come to that later if it is required. And here there are some examples of additive manufacturing. So this is one of the engines that is used by NASA for one of their rockets. So this is the thrust chamber, the nozzle part. From the thrust chamber, it is coming, the hot air is coming through this nozzles. Okay, it is exposed to very high temperature. So in order to cool them, so they require a cooling channels inside this nozzles. So for conventionally making this cooling channels are very, very difficult. So previously they were not at all making this cooling channels. Otherwise the shape was not like this. Okay, because if you look at it, see here, it is having a curved profile and they required a whole curved internal cooling channel in a curved way. Is it possible to fabricate through conventional way? You cannot drill it. Straight hole means you can drill it because it is coming in this way. It's a very simple shape, but we cannot make it. But additive manufacturing, we will be able to do that. So here you can see that this one they have made using laser powder DED process. Okay, feedstock is powder and source of energy is laser, and it is a direct energy deposition methodology. Okay, so that is fabricated. Here you can see that. See, these are the cooling channels, the cross section. And similar way, when they were making the similar kind of engines, small engines, In that case, when they were making in traditional manufacturing way, the design was like this, and the cost of production that was around $3,10,000 for one quantity, and the production time was, the lead time was somewhere around 12 to 18 months. With the help of additive manufacturing, they changed this design into this design, that is a better design. Okay, so that is more efficient. The cost is came down to 2 lakhs, and also the lead time also came down from a 18 months to came down to 8 months. And with the evolving additive manufacturing, with the more capabilities of additive manufacturing, you can see that the further the cost came down to $1,25,000, and the lead time is also came down to 5 months or even lesser than. Okay. So this is the lead time reduction which is happening with more efficient design with less time. This is another applications of additive manufacturing for making internal cooling channels. This is for a die making industry. This is a ejector pin in a dies. Okay, injection molding dies. So this particular component is experiencing high temperature. Okay, every time whenever they are putting out this hot component from the die to be out, they are having an ejector pin. Have you all understood with the dies? Like in the case of a casting, we do have a die. Okay, in the case of die casting. Similar way in injection molding, we do have a die. We are injecting the plastic or metal component or molten metal into it, and then once it is solidified, it has to be ejected out. For that, there is an insert is there. So this is that insert, and this insert is experiencing a every time when it is come in contact with the hot metal. Okay, so whenever it is keep on getting heated, there will be thermal softening, so that there can be a plastic deformation can happen or wear can happen, so it can deform very fastly. So what we wanted is we need to cool them. Okay, we need to cool them. So for that we require what we require. In order to cool that, what we require? In order to cool that, what we require? Don't sleep. Okay. In order to cool that, we require the cooling channels, internal cooling channels, without affecting its strength of it. Okay. So this is the component which is fabricated through additive manufacturing process. Okay. Here you can see that internal cooling channels. Okay. So this and all, without any complexity, without any additional process, we will be able to achieve this design change. So that is the advantage of additive manufacturing. And this is another advantage. The design, you can see that whenever we are making this component directly, its weight is somewhere around 4.6. When we are trying to redesign for additive manufacturing, its weight is came down to 1 kilogram. That means almost 78% reduction in the material. Okay, and similar way, if you are doing with the design for additive manufacturing, only for additive manufacturing, if you are designing it, again its weight can be further reduced into 0.4 kilogram. That means we are saving almost 91% of material. That means weight reduction in the design or in the component is another advantage of additive manufacturing. Okay. Can you wake him up? Can you tell me what are all the different advantages of additive manufacturing? What are all the advantages of additive manufacturing? Any two. Any two advantages of additive manufacturing. Less production time, not production time, less lead time. Lead time and production time, there is a difference. What is the difference between production time and lead time? Production time is a subset of lead time. Lead time means from the time you are started to conceptualize the product, design, iterations, then fabrication it, release into the market. That is the entire time is the lead time. Production time means only the manufacturing time for making that component. Okay, so production time is not less, only the lead time is less. Okay, production time is, many of the cases it will be larger in the case of additive manufacturing. Okay, so anyway, I am not going to compare the additive as well as subtractive and formative manufacturing process. I am skipping that. So the major advantages that we are getting over here is what are all? Weight reduction is there, part consolidation, that means multiple parts can be integrated into single component and we can make it. It is called as part consolidations, individualization, complexity is free. Then what else? These are some of the advantages of additive manufacturing process. I skip all these things. And if you look at the history of additive manufacturing or 3D printing, it can be divided into three major areas. That is its infancy period. Okay, that is the time period from 1981 to 1999. It is considered as 3D printing was in a infancy stage. I am not going into the details of happened. In 1984, the first SLA 3D printer, okay, that was discovered and patent. And based on the same technology, in 1987, the first additive manufacturing machine that came into the market by 3D systems. So all those things were there. And from 1999 onwards to till 2010, it is considered as its adolescent period. Okay, so many activities were happened in this time, and then from 2011 onwards till today, it is considered as the prime time of additive manufacturing. Okay, a lot of breakthroughs were happened, a lot of lab grown organs were released in, started produced it. So many things were happened. And now let's forget about all these histories and advantages and etc. Now let's come back into additive manufacturing methodology. Okay, so when we talk about additive manufacturing, it is having three different stages. One is pre-processing, another one is processing, another one is the post-processing. Okay, post-processing. So pre-processing stage, basically what happens is that the conceptualization of 3D component that we want to, you have to design it. Okay, you have to make a 3D model in a CAD software. Okay, once you made this 3D model, then you need to convert that 3D model into STL files. Okay, what is STL files? What is meant by STL files? Slicing, but what is the full form of STL? So the direct step file that on which you are making your CAD files, because the CAD files what you are making, that is normally it will be in step file format. That may not be suitable for additive manufacturing. It need to be converted. It need to be converted into STL files. STL file is called as standard tessellation language. Okay, it is not stereolithography files. So that is also a name. Very often we used to say that. That is based on the first additive manufacturing technology, because this STL file is used for the first additive manufacturing process, that is SLA. Okay, that is a stereolithography. Okay, so we usually call it as stereolithography files, but actually it is standard tessellation language. We need to convert the step file or the CAD file into STL files. So what we are doing in that stage? We are dividing the all surfaces in your CAD model into small triangles. Okay, and then we are saving the informations related to the three vertices of your triangle, the normal of that particular triangle. Only these informations only we are saving it. Okay, so that also I am not going much deeper into it. So we need to convert the file into STL files, and after that you need to slice them. After converting STL file only, we are slicing it them. Okay, that means we are converting the entire model. If this is your model, then we are converting that into small layers. So once you make these layers, you have to identify the contours in each slices. Which contour is having the material and which is not having the material. And then once you identify that, then you need to generate the NC codes for each of the positions on this contour. Because you need your 3D printer head has to move on to these locations and need to deposit the material, isn't it? So for that purpose, you need to generate NC codes. That NC code only we are sending into the 3D printer or additive manufacturing machine. All these things are happening in the pre-processing stage. Okay, this much activities are doing in the pre-processing stage. And then once these NC codes are ready, then we are sending that NC codes into different machines, or we are sending into different processes. Okay, so that process, according to ASTM, there are 7 processes. Each process is working in a different ways. Okay, each process is working in different ways. It's having different technologies. So in the market, there are almost 30 or even more than that technologies are there. But ASTM has identified and recommended or identified and named them, or in the list of additive manufacturing, it's only 7. It may be revised maybe in the next year or in the years to come, it will be revised and they may include more additive manufacturing into it. But currently, at this moment, we do have only 7 additive manufacturing technologies according to ASTM. So once we do that, then we do take the component out, then we may require to do some kind of post-processing operations over there. Why we need to do the post-processing operations? Because the properties of the component that we are getting through additive manufacturing, it may not be same as that of the way we have fabricated through conventional ways. Sometimes it is superior, sometimes it is inferior. Okay. So in order to make them same, we may have to go for some kind of post-processing operations. And another important thing is that the surface finish that we are getting, okay, that will be like a cast component. In a general way, we do say that it is like a cast finish only we do get through additive manufacturing. Okay, it's not true, but to some extent it is true. But by optimizing the process parameters and all, nowadays we will be able to get a better surface finish. Okay, but we do generally say that we do only get a cast finish. Okay, so that we need to do a post finishing operations need to be done. A post finishing operations is required. And not only that, whenever you are making the components, in some scenario, we may have to provide a support structures. We may have to provide a support structure. Support structures means, suppose if you want to make a component like this, an L-shaped component, you are fabricating it. Like that, now when you are trying to make this, the first layer of overhanging structure, so there is nothing in the bottom. Then where you will deposit? You don't have platform to deposit the material. So you need to build something from the bottom to this height. This will provide us a platform for you to deposit the material in the overhanging structures. Okay. So this much portion is called as the support structure. Whatever you are additionally building, that is called as structures. The support structures are not the part of your component. So that need to be removed finally. That need to be removed. Okay. So that support structure removal is also a post-processing operations. And not only that, whenever you are trying to make a component this way, the mechanical properties as in this direction and in this direction will be different. Okay, it will be different. That means the dimensional anisotropy will be present in the additively manufactured metal parts. Not only metal parts, in polymer parts also. It is because here you are applying on the layers, because you have layers, you are applying 90 degree to your build directions. When you are doing it in this way, you are giving it in this direction. That is not 90 degree, I mean 0 degree to your this one. So property will be different in these two directions. And through research it is found that you will be getting better properties as in 45 degree. You will be having a better properties in this directions. Not 0 degree, not 90 degree, in between. Okay. So we need to make them same. Okay, because when we are designing any components and when we do the design analysis, we were considering that the property is uniform in all the directions, isn't it? Whenever we are doing the ANSYS analysis, what we are considering, the property is same in all the directions. Okay, so we need to make them in direction. So all these things we required lot of post-processing operations. Not only that, the residual stress getting formed within each layer, that will be different. Okay, every time we are heating and melting and depositing one layer, then the next layer is again melting and depositing. So that time the bottom layer is again getting and deposited. And not only that, so across the layer as well as within the layer, there is a temperature gradient present. So that will leaves you with lot of thermal residual stresses. Okay, these thermal residual stresses need to be relieved. So for that, we need to go for a stress relieving operations. That means stress relieving heat treatment may be required. So that is also considered as a post processing. So in this, so tomorrow onwards, Professor Mario will be telling about how we will be able to use short peening as a post-processing technique for metal additive manufactured components. Okay, metal additive manufactured components. So if you look at it, so why do we need additive manufacturing? If you look at this graph, you can see that it is assumed that almost 32% of the product that's sold in the market now, that will get disappeared in another 5 to 10 years, and 38% of the product that you are seeing now, I mean sold in the next decade, that won't be able to conceptualize it now. That means additive manufacturing is going to drastically change the components availability. Okay, it is going to get completely changed. And this cycles and also I am skipping it due to time restrictions. And here you can see that what are all the benefits of additive manufacturing, like complexity is for free, simplification of part fixturing, reduced turnaround time, mass customization, integrated components, material freedom, logistic freedom, and reduced material wastages. These are all some of the advantages of additive manufacturing. Okay, so some of the limitations, whenever you are trying to make a curved surface through additive manufacturing, it leaves you with the staircase effect. So here you can see that when you are making one layer, then when you are trying to make a next layer, you can see that there is a formed. This is only happens whenever you are trying to make a curved surfaces. Okay, then along with that, some of the high production cost, mechanical properties is like I have told that it will be having a dimensional anisotropy, requires post-processing, limited component sizes. Currently, we do have a limitation on the size of the components. We don't have large machines. Okay, but nowadays people are started making it. Some companies they are started making a bigger machines. Then stair stepping effect. That is also another disadvantages of additive manufacturing. So now, according to ASTM, okay, F42 committee, that is called as 52900, we do have around 7 additive manufacturing technologies. Let's start with the first one, that is the watt photopolymerization. So this is the first technology that is based on the SLA, that is stereolithography. Okay, so based on a photo curing of the material that came into the market. Then we do have material extrusion. that is called as the FDM technology, that is fused deposition modeling, FDM. But ASTM says that we should use the word FFF, that is fused filament fabrication. FDM is a trademark name of one particular company that belongs to Stratasys. Their model name it is FDM. According to ASTM, the technology is called as fused filament fabrication. Then we do have another technology that is called as material jetting. Okay, the third technology according to ASTM is material jetting. Then we do have another technology called as binder jetting. Then we do have direct energy deposition. Then we do have sheet lamination. And then we do have powder bed fusion. So these are the 7 technologies as according to ASTM, which is categorized under the additive manufacturing. So today I wanted to introduce you with this powder bed fusion, that is the first technology on additive manufacturing process. Okay, and that is also having a highest level industrial maturity. This process is obtained the highest level of the industrial maturity. That means 5 out of 5 it is reached already. Doesn't mean that no research is not required. Research is required in that level further. Okay. So in metal additive manufacturing, so currently around this many technologies are there, but I am not going into the details of all these technologies. So many technologies are there, but it is all of them are not listed in according to ASTM. It may be listed in the future. Forget about all those things. Let's focus on laser powder bed fusion. So laser powder bed fusion comes under the metal additive manufacturing, and also it comes under the melting based process. Here the different material is getting deposited by melting the feedstock. Okay, by melting the feedstock. Here the feedstock is powder. That's why it is called as powder bed fusion. Okay. So based on the melting process, that can be divided into 2. There we do have powder bed fusion as well as direct energy deposition. We do have 2 different categories. In that powder bed fusion, again we do have 2 categories. One is when we are using laser beam, then that is called as laser beam based powder bed fusion, and we do have another one, that is electron beam based powder bed fusion. Okay. So we are talking about the laser beam based powder bed fusion for today, just for another half an hour, and I will just introduce this particular technology, how it works. Is it okay? Any doubt till this time? Any doubt? I am happy that no one is sleeping. Only 2 people only were dared to sleep. Now they are also not sleeping. Okay. Any doubt? No. You understood everything about additive manufacturing. Can you tell the definition of additive manufacturing now? How do you define additive manufacturing according to ASTM? The process of joining the material to make a 3D object in a layer by layer fashion from a digital model, as opposed to subtractive or formative manufacturing process. Okay. Here you can see that this is what I was telling about, that industrial maturity level. It is not that clear over here. Here you can see that lot of additive manufacturing process, and this is 5, that is in a scale of 5. Okay, that is the technology maturity level. That is in the x-axis it is showing as technology maturity level, and the y-axis is showing that industrialization index. Okay, so this is the location where we do have laser powder bed fusion. Okay, so it has achieved 5 out of 5 in the case of technology maturity index as well as in the industrialization index. Okay. So when we are talking about metal additive manufacturing, different heat sources can be used for it. So we can use lasers, we can use electron beam, we can even use the welding arc. That also can be used for additive manufacturing. So that time it is called as wire arc additive manufacturing. Okay. So based on that also we do have additive manufacturing technologies, hybrid heat sources. Okay. So this is how the laser powder bed fusion process schematically looks like. Okay, schematically looks like. Have you ever seen this technology before? Have you ever seen this? Okay, so here you can see that there is 3 chamber. Okay, 3 chambers. So initially this build platform will be on top of it. Assume that it is here. Okay, initially it will be on top of it. So what happens is, here we do have a piston. So this moves up. So when this moves up, this powder particles that will come in front of the roller. Here you can see a roller over here. Okay, when this moves up, some powder particles will be in front of the roller. That time the roller will be moving from left to right. So what it happens? It takes the powder particles in front of it to be spreaded on this build platform. This build platform will be initially in the top of it. So this roller will be spreading the powder on top of this build plate. That is called as the build plate. What is it is called? What it is called? Build plate. So it will be spreading the powder particles on this build platforms. Okay. And excess powder, after spreading the powder particles on the build platform, that will be deposited over here. Okay, in this chamber. Okay, so that will be collected over there. So what happens is, based on the CNC codes which we have generated previously, so that CNC code, according to that CNC codes, this laser beam, this is the laser source. We do have lot of optical lenses, and this laser beam will be spreading this lasers on, or selectively going onto your build platforms and fusing them. Okay, so wherever the laser beams are coming in contact, so that will be melting, that powder particle will melt and deposit. Only the place where the laser beams are coming in contact, that will get melted and deposited. Okay, so then once it is completed, this one moves down, then this goes up, this powder particles will come from here to again on the build platform. It's keep on repeating this process, and finally you will get your component fabricated in a, or it is submerged in a powders. Finally the 3D component will be completed and it will be submerged in a lot of powders. So you have to clean the powders and take the component out of it. So whenever you are having the laser beams are coming in contact, here you can see that it is getting melted. Okay, it is getting melted and it is getting solidified. So the new microstructure is getting developed. And the grain growth directions also you can see that it will be moving in this way. Okay, that's how it is happen. I hope you guys understood how it is working. The working of a laser powder bed fusion technology. Okay, so the whenever this laser is coming in contact with the powder particles, some is getting reflected, some is getting absorbed, and some is getting transmitted. Okay, so that is how. So whatever the laser energy is getting absorbed, that only will be utilized for increasing the temperature, and finally that will be responsible for melting your powder particles. Okay, so this is how the laser powder bed fusion process works. And if you look at over here, see, whenever a laser beam in coming in contact, so it will melt one layer of powders, and whenever it is getting melted, there is lot of fumes are getting generated, and some of these fumes that will get entrapped inside that layer itself. You can see that some of the layers, some of the fumes are getting deposited over there itself. It is a simulation. Okay, the laser beams are coming and it is melting the powders, and while it is getting melted, this alloying elements is, some of the low melting point alloying elements is may get vaporizes, otherwise some fumes are getting generated. These fumes are getting entrapped inside your layers. So that means the component that we are fabricating, that will be having a residual stress that we have seen that how it is getting generated because of the thermal gradients. It will be changing within the layer as well as across the layers. In addition to that, we do have these kind of, here you can see that these kind of small spherical or different kind of shapes, pores are will be present. Is there any problem because of this? What kind of problem? It will be voids. How it will be uh, influencing on our properties? How it will be influencing on the properties? It will change the mechanical properties. How? It will significantly influences the strength, not exactly. Small pores. Okay. It will influences the fatigue properties if it is on the surface or in the subsurface levels. Okay. So that's why additive manufacturing, lot of fatigue tests are conducted because these shapes are getting, the different shapes are forming and it is located on the surface as well as in the surface levels, and it will not give you a consistent fatigue material behavior whenever you are trying to make it through additive manufacturing. It may be different in different times because the different times different kind of pores will be forming. So its influences on the stress concentrations or its propagation of the cracks, everything will be different. So it will be leading to an inferior fatigue properties, is not only inferior fatigue properties, is the mechanical properties, as we can say that. Okay, we will be getting a different properties. And here there is a diagram, I mean a video to make you better understand how this laser powder bed fusion works. Very small powders are used for making the laser powder bed fusion components. Very fine powders. Okay. So whenever the laser powders, I mean the laser is coming and interact with the powders, we will be able to get the components. But it is audio is there, but it is not possible to be projected here, the audio. This is the way they are loading the powder into the machine. Okay. So here you can see that the laser is interacting with the powder bed, powder particles, where it is becoming solidifying. You can see that is making solids. Okay. So once one layer is done, the next layer is coming on top of it. Again the laser is scanning. Okay. So once it is done, then we have to clean it and take the component out. You here can see that. So now the made component is submerged inside that powder. You have to take out the entire chamber and clean it so that you can take the component out. Okay. So that is how this process works. Okay. So they are closing the chamber. They are taking the entire, so different of methodology. So in this, they are closing it and they are chamber out. And then using a vacuum cleaner, taking all the powders out. So that finally you will be getting the component inside. Okay, the 3D inside. This for Now they are started to take the powders. Okay, suck the powder using a vacuum cleaners. So once it is done, you will get the component. You can see that. So whatever the design that is there out in it, that was submerged in a powder initially. Okay, so now you can take it out and wire cut it. You can do the finishing. You can see that the surface finish of it, it is not so finish. It is like looks like a cast finish. Okay. So we will be talking about the laser powder bed fusion. Here it is full melting is the mechanism that is most commonly associated with the laser beam based powder bed processing. Okay, it is in the case of almost all kind of metals and alloys, and also we are using it for some kind of polymers as well. So that time it is called as SLS process. So the entire region of the material is subjected to impinging of the heat energy, and wherever the laser is coming in contact, that will be melted to a depth exceeding its one layer, because it has to melt with the, or it has to join with the previously deposited layers. Okay, so that means we do say that normally 30% of the melting of the previous layer is happening, and thermal energy of subsequent scans of a laser beam is sufficient to remelt the portion, that is the 30% of the previously solidified structures. Okay, and this full melting is very creative, or to form a creating a well bonded and high density structures from almost all kind of metals as well as for polymers. Then rapid melting and solidification of this metal alloys results in a unique properties like we have said previously. It will be forming a different properties, a unique properties that are distinct from, and can be sometimes it may be desirable in some of the cases, and sometimes it may be different, or it may be inferior, and sometimes it may be superior. So we have seen that the wear properties are, we do have get better properties, okay, but the other properties may be difficult, I mean it may be inferior. For example, fatigue properties are normally inferior, and all metals may be thought as a candidate for a material, but there is a large difference exist in the case of processing of it. That means in terms of the laser absorption, in terms of the surface tension and viscosity of the liquid metal, etc. Each metals are different, or each alloys are different, and that need to be process parameter window that need to be found out separately. That means for each new material, a process parametric window that need to be determined experimentally or numerically, okay, in order to avoid the scan track instabilities, okay, or other kind of bowling effects or other kind of difficulties. In essence, I want to say that for whenever you are trying to do a new material for additive, especially for laser powder bed fusion, the process parametric combinations that need to be found out separately. So whatever it is working for titanium, that may not work with inconel or copper, or sometimes whatever it is working for copper, that may not be suitable for other materials. So in the case of copper, the reflectivity of the laser absorption capability, let's put it in this way, the laser absorption capability, that is very, very less. The most of the energy will be reflected away. But the titanium is having a very good absorbability of laser, so it is very easy to process in laser powder bed fusion. That's why in the initial stages of the development of this technology itself, this laser, I mean the titanium as well as, inconel materials are very common. But that is very difficult to be processed in conventional manufacturing methods. But it is easy to be processed in, to some extent, it is easy to be melted in laser powder bed fusion. But copper, it is very difficult because the energy is getting reflected away. The laser energy is getting reflected away in the case of copper. Okay, not only in copper, aluminum is having 660 degrees Celsius as the melting point. Titanium is having a melting point of somewhere around 1500 degrees Celsius. Titanium can be melted easily, but aluminum alloys are difficult. Again, it is because of the reflectivity of the powders. The energy is getting wasted, reflected away. That's why we don't have varieties of aluminum alloys cannot be processed. We do have a variety of aluminum alloys, 6000 series, 5000 series, lot of aluminum alloys are there, but these are all not yet developed for additive manufacturing technologies. We do have very few aluminum alloys can be processed in additive manufacturing. One of them is ALSI 10mg, one of the silicon alloys, so aluminum silicon alloys that can be processed. But other aluminum alloys are not processable. One of the major reasons for its reflectivity. The laser beam is getting reflected away. And if you look at this powder bed fusion, these many process parameters are existing over there. So some of them are laser related parameters. So that is the laser power, spot size, pulse duration, pulse frequency. All are related with the lasers. All these are important. And similar way, scan related parameters are there. That is scan speed, scan spacing, scan pattern. Okay, all these are related with the scan related parameters. So powder related parameters are there. The particle shape, size and its distribution. The particle shape, whether it is a spherical or irregular shape, okay, all these are important, and the size of it is important, and how it is distributed, that's distribution, the size distribution. Because whenever you are taking a powders, all the powders won't be having a same size. Okay, it will be having a, none of the manufacturers will give you a powder exactly as 40 micrometers or 80 micrometers. They will say that it will be varying from 40 to 100. Okay, how that is distributed in the total powder, that is really important. Okay, that is particle shape, size and distribution. Then powder bed density, the layer thickness and the material properties of those powders, all those are important. Then we do have temperature related parameters, that is the powder bed temperature. When the laser beam is coming and hitting on the powder particles, what is the initial temperature that you have maintained on the powder bed? That is important. So that will help you to reduces the temperature gradient, so that the residual stresses getting formed will be lesser. Okay, so that is one thing. Then powder feeder temperature and temperature uniformity, all these things are very important. These are some of the process parameters. Here you can see that again the schematic representations of these things. So here you can see that the distance between the two tracks is called as hatch distance. Okay, distance between the two tracks is called as the hatch distance, and the scan velocity means at what velocity this laser beam is moving. Okay, so that is scan velocity. Then the layer thickness is the distance between the two subsequent layers, the height of one layer. Okay, this will be exactly same as that of in the pre-processing stage. How did you slice it? Okay, how did you slice it? So that will be matching with this. And here you can see that, see the interactions between the scan velocity as well as the power of the laser, the source power. See, if you are doing it in this region, that means scan velocity is less and the source power is in this region, you will end up with a keyhole porosity. Okay, you will end up with a keyhole porosity. Keyhole means your laser will be penetrating too much into your powder bed. That means it will be reflected inside your melt pool. The laser beam can get reflected inside and it will be reaching a higher depth than that of your layer thickness. So it will be resulted in a keyhole melting. That means it will be going deeper and getting melted. Similar way, if you are having a very high scan velocity and very less power, then you will be end up in this region where the powder particles might have not fused it. It might have not even melted. So similar way, if you are having the scan velocity, high scan velocity, and somewhere around this laser power is in this region, that means very high to a medium level, then you will be ending it with Bowling phenomena. Okay, I'll show you pictorial representation of what is meant by this Bowling phenomena. Okay, that is again physically damage your recurrent blade or the rollers, or even it may interrupt the process, it may stop the process in between. What is Bowling phenomena? What is Bowling phenomena? What is bowling? What is bowling? What is bowling? I'm asking you. What's your name? Yes? Srikutan. Srikutan parayu. What is bowling? What is meant by bowling in laser powder bed fusion? Have you heard this before? No. Okay. Listen carefully so that you can understand that. So normally in a powder bed fusion, there will be two galvano setups, okay, galvanometers that will be reflecting your laser beam in both directions. Okay, in X direction one, another one for Y directions. Two galvanos will be there, and similar to stereolithography, the scanning often occurs in two modes. One is in contour mode, another one is in fill mode. Okay, in contour mode, you will be scanning the contours first, and in between you will be filling your lasers. Okay, it is same as that with SLS process or SLA process. Okay, in contour mode, like you are seen in the slides, it will be the outline of the part cross section of a particular layer is scanned. That means initially the outer layer will be scanned. Okay, so that is for the better accuracy as well as for the surface finish around the surfaces. Okay, so that is contour mode. So whatever the surface, suppose if I am making one layer of this particular thing, initially it will be scanning the entire outer surface. Okay, in the fill mode, we will be scanning in the, after that only we will be scan only in the inner surfaces. So it gives us lot of, better surface accuracy or surface finish we will be getting on the outside of your contours. Okay, and after that we will be dividing them into small islands like this. Okay, small islands, and in this island also the scan strategy, the scanning will be changing it. This is to randomly distribute the stresses getting formed. Okay, so here you can see that. So in this particular square, the residual stress distribution will be different, but when you are doing it in this way, it will be different. So this is how the laser powder bed fusion machine works. Okay, so this is for random distribution of the residual stresses which should not be applied in any direction. Should not be in any specific patterns. So that is one of the reasons why we are going for in this way. And here also you can see that. So if one layer is fabricated in this direction, when it comes to the next layer, it will be in a different way. The laser will be scanning in the different ways. All these things are influencing your final properties of the component. Doing it. Okay. So finding out an optimum strategy itself is an important task. okay, for different materials. So some strategies, this is called as the scan strategies. So this strategy we work for, maybe work for one material, it may not work for another material. So another thing here you can see that, so here you can see that the over melting is the overlap between the previously deposited layers. This is one layer. When it comes to the next layer, there is an overlapping. Still you can see that there are some kind of holes. All these are end up with some kind of porous structures because there will be unmelted powders will be there. So whenever we are dealing with additive manufacturing, especially laser powder bed fusion, we do end up with the defects like porosities, small structures, and also we will come up with unmelted powders in between. It's not mandatory. Our intention is to have less porosity as well as less unmelted powders, because this unmelted powder particle that can be act as a stress concentration points and the fatigue crack can initiate from that particular points. Like you have seen in yesterday's class, in yesterday's first two classes, you have seen that. So after the fatigue component is failed, they are finding out the from where the crack is initiated, isn't it? Do you remember that figure? So they are finding out. You have seen that some sandmark or beach-like structures and also before that it's all are initiating from one point. So that unmelted powder point can be a location from where the fatigue crack might have initiated. In many literatures it is shown that these powder particles are starting from, like the cracks are getting propagated from these porous structures or even from this unmelted powder regions. And in fill mode, like I have already told that the common fill pattern is a rastering techniques whereby one axis is incrementally moved a laser scan width, and the other axis will be continuously stepped back and forward for being a printing the components. Like means we will be having a different structures like we have seen this. Okay. So that is called as the fill mode. And random scanning is often utilized so that there is no preferential direction for the residual stresses induced due to the scanning. So this is what I have previously told, that we will be always doing a random scanning. That means we don't want the residual stresses to be induced by the scanning in one direction, any of the directions. So the use of random square based strategy is the primary for the metal parts, and symbol raster pattern for the entire part is typically used for the polymers and other low melting temperature processing. And here you can see that some of the problems is that we are encountering on laser powder bed fusion, that is keyhole porosity. The primary approach is to reduce the laser power. So if you are getting a keyhole melting, that means a deeper layer thickness you may be getting it. So it would be better to reduce the laser power. Okay, the secondary approach is also there. Even you can increase the laser velocity, obviously it will be equal to the reducing the laser power. And similar way, you can see that the multiple problems, that is the lack of fusion porosity, then composition change, that means low melting point alloys can get evaporated, because in the case of a Ti6L for vanadium, if you take it, titanium is having a high melting point and aluminum is having, what is the aluminum's melting temperature? What is aluminum's melting temperature? The last one. You tell it to me. I'm asking you. I already told here. What is the melting temperature of aluminum? It is somewhere around 660 or in that range, depending upon the alloy, it will be changing it. So that even get melted and vaporized, but titanium is getting on your additively manufactured component. And residual stress and its distribution. Okay, so one of the strategy we are using is reduce the scan vector length. That means we are the track length will be very, very small, and we are the heated substrate or the chamber, that is another strategy for reducing the residual stresses. So similar way, we do have powder related parameters. Okay. So then temperature related parameters we do have, like I have seen previously. Okay. So whatever I have listed previously, I am just given the explanations. So I'll give you the printout of so that you can read through it. And this is how we are getting the laser tracks whenever we are using a continuous wave as well as a powder, I mean the pulsed lasers. But even in the textbooks and the literature says that the pulsed lasers are more powerful and it gives better results. But we do have very few companies, only one company. They are only started producing the machines with pulsed lasers. But in almost all other cases, it is a continuous wave lasers only. And the influence of bowling phenomenon. Here you can see that what is meant by the bowling phenomenon. Where we are, the normal case, it will be like this, the powder will be spreaded, and in the case of a bowling phenomenon is happening, you will be getting whenever this layer is getting melted, you may be getting the bigger balls. The powder particles will be fused together and it will form a structures like balls on your build platforms. And when you are trying to spread your next layer, you see that whenever you are trying to spread the next layer, the recorder blade will be going up and down. Okay, it will be going and up and down. In this case also there is no problem, only just going up and down. But you see that if it is end up in end of conditions, so this process will be in between. The laser recorder blade will be stopped by the balls, and it will, the process will be stopped over there. Okay, so this is the bowling phenomenon and the energy correlations, and finally the residual stress distributions. As I have already explained how the residual stress is, that in order to reduce the residual stress impact or randomly distributing the residual stresses, so we are using different scan strategies. Here you can see that the residual stresses and the subsequent part deflection increases with increases in the track length. So in order to avoid that, we are using a very small track length, that means in infill mode, and that also we are changing it in the different layers. Okay. And with this, I would like to wind up. And in order to avoid this or overcome the residual stresses or these kind of defects, so I told that there are two major reasons. One is the fatigue strength, that is comparatively lesser for additively manufactured components, and also it is inconsistent. And it is inconsistent. So in order to improve that, we are using short peening. Okay, and also to change the tensile residual stresses which is getting formed on the surfaces to compressive residual stresses, in order to these two reasons, and also to improve the surface properties or surface roughness. So we are using the short peening. We require the short peening. Okay. So tomorrow he will be majorly talking about the metal components and the impact of short peening on this additively manufactured components. At least, now additively manufactured components means it is not only laser powder bed fusion. We do have DED, we do have binder jetting. Similar way, so many other metal additive manufacturing technologies are there. But he will be mostly talking about, more focused on laser powder bed fusion. That is the reason why I introduce you the laser powder bed fusion. Okay, as you are, majority of them are BTech students, I thought that you may not be aware about additive manufacturing. So my intention was to introduce you what is additive manufacturing, and one process we have learned in detail, that is laser powder bed fusion, and some of the disadvantages which we have seen today, that he will be trying to overcome through applying the short peening process. Okay. And also, I think in tomorrow's afternoon lecture, you will be seeing that the influence of the laser short peening on the laser powder bed fusion components. Okay, even laser short peenings are there, so that will be. If you have having any questions, please let me know. Any questions? People those who are asking questions are not here. Why you guys are not asking any questions in yesterday's and today's class? Either it is you have understood everything or you didn't understand anything. The questions are asked by only very few people, isn't it? Not even a single question from a BTech student yesterday and today. Why? Normally it is happening in the other way. BTech students used to ask a lot of questions. No questions. Now also no questions. Applications, aerospace, industries. Like I have shown in the beginning, right? Beginning I have shown you so many components. So all those are applications. See, this is one of the application of additive manufacturing. This is another application of additive manufacturing, and this is another one. Okay, this is another applications. In general, I can say that it is having applications in aerospace, biomedical industries for making implants. Okay, patient specific implants. Suppose if someone has got an accident, he got a fracture over here. Okay, so the doctors wanted an implant over here. Okay, on the skull. So they cannot take something which is already available in the market because he has got a fracture. Okay, that is different. So they can take a CT scan, they can make a CAD model, they can redesign the shape, then they can 3D print it, they can do the post processing and fit it. One best example for that. Okay, nowadays it's happening. Okay, nowadays it is happening. Hospitals in Kerala, they are doing this. So, but they are fabricating it in outside Kerala. They are sending to Bombay or Bangalore. So they do 3D print it, finish it, and send back. And in Kerala, they are implanting it. And also in aerospace industries, a lot of components are getting fabricated nowadays using additive manufacturing because it is having part consolidation is one of the advantage. In any of the designs, we don't prefer joints, isn't it? We don't prefer joints. So if you can make without joint a component, it would be always good. So that part consolidation gives a lot of advantages in aerospace industries. And nowadays in automobile industries, so Volvo, what they're doing is that for their some of the engine components of older engines, which is the machines, I mean the vehicles are already there, it is functioning, but they stop the production. Okay, what they if they get an order for making those components again, what they do is they do 3D print it. They do make a single component through 3D printing and send them back to the customers. Because the model, so no production of those components. So one only they require it, they do it. Okay, these are all some of the advantages of metal 3D printing. So ours is more concentrated on metal 3D printing. Okay. Any other questions? Bowling effect. So that I have shown, right? That graph. I'll give you the printout of it. So you can adjust the process parameters to some extent. See, you have to make sure that you are making the component over here. your process parameters are selected in this range. Okay, so that means if you are feeling that the balling is happening, either you can reduce the scan velocity or you can reduce the power. And different strategies. This is one example. Okay. And I hope that from tomorrow onwards you will be asking a lot of questions. Okay. So he also prefer to have lot of questions. He is telling me that see he will be comfortable or he will be happy only if you ask the questions. Not only him, every teacher will be comfortable when you guys are starting to ask lot of questions. You keep on asking the questions, so he'll be so happy to answer it. Don't feel that if you're asking questions, he will be get like annoyed or he will be having a difficult time. No, keep on asking the questions. Okay. So if it is no further questions, then we can go for tea. Okay, and after that, you will be visiting the school of not school of the Department of Material Science and Engineering's laboratories. Okay, and after that, I think you need to come back over here, isn't it? You have to come here and you have to decide your teams for the presentations. Okay, so it has to be a joint team. Don't make a team from your own institute. Okay, you have to take it from different institutes, get to know each other. Okay, so work on those problems you have tonight, tomorrow, and day after tomorrow. Okay, so 3 full nights it's with you, so you can make the small PPTs, maybe 4 or 5 PPTs. All of you are having laptops, 4 or 5 PPTs you make it. And now you are having the internet connection, you can download the papers, whichever you wanted, download it, make 3 or 4 images from that, come and explain it. Okay, related to short peening. Okay, related to short peening and additive manufacturing. Okay, thank you.